Okay, one more example in class number 2. All right, class number 2. Here's an example. This is from the 8th edition. This might actually be a problem in Johnston's most recent book as well, but we'll go ahead and pretend like it's an old problem. So we have these two blocks. I think I've redrawn them from what's in the book. And at this instance shown, B is moving with a constant acceleration and its speed is 6 inches per second. Knowing that after A has moved 10 inches to the right, its velocity is 2.4 inches per second, determine the accelerations of A and B and the velocity and change in position of slider B after 4 seconds. So there's a lot of stuff going on. So we really have to be careful and organize our thoughts because it could get overwhelming with all these things going on. So we need to systematically break the problem apart. All right, so there you go. So what to do? Well, we want to do a datum first. So let's make this one of our datum. We're going to have to make multiple datums, but this would be a good place to start right here. And right here, I'm going to do a reference to right there. And I'm also going to go to a reference to right there, right? So here's going to be something we call XA. And here's something that we call XB. Right? Now, this is a little confusing right in here. So one way that will help us to try to figure out the lengths of these is to make another distance. And I'm going to make a distance right here that I'm going to call C. C wall is what I decided to call it. All right. So we can see that we have one single cable, right, stretching all the way through there, right? But if we want to let's get this length first, right? That's the easiest one. That's just going to be the length XB. There you go. That's XB. The length of this guy. Now let's go back. Let's figure out the length of this one right here. Well, that's going to be XB minus XA, right, for that length. So I'll go plus XB minus XA. Okay, now we have this length and this length, which will be equal to each other, right? And are going to be C wall minus XA. So 2 C wall minus XA. Now, before we take the derivative of this, we could just lump everything over here into one constant. We could lump this constant, so 2 times C wall can go back over to there, and we could just say C, right? And that's just a total constant. Well, let's say we have 2 XBs minus XA, but there's another 2 XA right there, so minus, so this goes 2 XB minus 3 XA. Easy once you see how it's done, but you have to think your way through this. Like, you know, this right here was really the key to seeing that, like, okay, well, we have this constant. Let's go ahead and use that as a means to try to figure out this relationship, which we know that when we take the derivative of it, it's going to be 2 times VB minus 3 VA, or the acceleration 2, acceleration of B, minus 3 times acceleration of A. From this, we know that the VA is going to be equal to 2/3 VB, and AA is 2/3. And it's not negative, right? It's because that negative made it so that they're going to be moving in the same direction, is what we end up saying. Interestingly enough, like we move this one in that direction, and this one also moves in that direction by 2/3 of the speed. So from the let's go back to the information they gave us, right? They said at the instance shown, B is moving with a constant acceleration, which we don't know, and its speed is 6 inches per second, right? So let's say at t equals 0. So this is at the instant shown, but now they're going to go 4 seconds later. So at t equals 0, we know that VB is equal to 6 inches per second. And I should say it moving to the right. I think I just forgot to put a thing in there. All right. So we could also say, and let's call this time 0, right? VB 0. And so we also know what VA 0 is going to be. That's just going to be 2/3 of that, right? Which is 4 inches per second, right? Now they tell us, knowing that after A has moved 10 inches to the right, its velocity is 2.4 inches per second, right? Now we can figure out what the acceleration is there. And it's acceleration because we have a velocity and a position, right? So let's use VA squared is equal to VA naught squared plus 2 acceleration of A, and they go delta x, right? Now we're going to be able to figure out the acceleration of A. So we put these in here, and it says VA is 2.4 squared, but it started out, did I say A? I think I meant, it says, knowing that here, that A, okay, yes, so to A. So that's the 4 squared plus 2AA, and it has moved 10 inches. We work that out right there, and if I'm correct, I think, right, that I have negative 0.5120 inches per second squared, right? So that's the acceleration of A. If I know that, I also, obviously it's decelerating, but I know this, I know what the acceleration of B is going to be. Acceleration of B is going to be 2/3 of the negative 0.5120. And that, according to this, is what? 2/3? Nope, should be 3/2. Yes. My bad. Because that's 2/3, but we're looking B, and this is acceleration A, so it should be 3/2. So a negative 0.768 inches per second squared. Did I round anything off? No, there was a 0 in there. Okay, good. And so that's part A right there. We wanted these two values. We got them. Now let's go with part B, the velocity and change of position of B after 4 seconds, right? So velocity, so this, by the way, this is not necessarily the same time as that, right? That is not the same position here. So we need to find a new velocity for this right here. So the velocity of B is going to be equal to the initial velocity of B plus the acceleration of B times time, right? So that initial one was going to be 6. Let's say it was B, right? Yep. 6 plus a negative 0.7680, and then they said 4 seconds. And so that comes out to 2.928 inches per second. And now if you want the position change, I'm just going to stick both of them, the x's over there, right? Normally it's going to be x is equal to x naught and then the rest of it, but I just move that x naught over to the side and say this is the change in position, so that's good enough. We're going to say that it's VB naught times t plus 1/2 AB t squared, right? So we know that that's going to be 6 times our 4 seconds plus 1/2 times r. This is b, negative 0.7680, and then a 4 squared. So we have the change of position is now going to be equal to 17.86 inches. So if we want to summarize all these answers here, A is going to be the acceleration of A is 0.512 inches per second, and I'm going to put an arrow in there. Acceleration of B, 0.768 inches per second, right there, right? And for B, we have velocity of B is going to be 2.93 inches per second, and it's still going that direction, and the change in xb is going to be 17.9 inches in that direction. This is a good problem. It's got a lot of things going on, and you could go back to reflect on how difficult it seemed when you got up to here. But you can see by methodically picking apart the thing, trying to apply some logic, it was really this guy right here that was probably the key to get us unconfused about how to get the length relationships. So that is another example we have down. All right. On to class 3.